Exciting. So we have everyone there. Um, so we are, we download all this data. We are focusing on TW Hydra, and we have, as far as I can tell, 92 files, I think. Yeah, 91 files. And and by now, I just want to know if we are all okay with the radio velocity corrections or with the shifting correction. If not, if we are close to at least understanding, in the case of um, you guys, I know Ognian is trying to get a package with a Python part, so that you guys can be at same steps. So it's all good,
Yeah.
right? Okay.
Yeah, so Ogden actually sent an email today. I think, or no, yesterday night. He sent an email. His code is object oriented, which is actually very nice. And so yeah, he said like it includes like both the spline interpolation and the cross correlation technique. So
Okay.
it works.
Okay, so now I think the next step is to get veiling, or at least the distribution of veiling across the wavelength determined for most of the stars. I mean, that's the first thing we do, because if you go to the stars themselves and just measure emission lines, these emission lines are masqueraded because of veiling. So veiling affects the measurements not only of the absorption lines, but emission. So which means when we know what the veiling level is next to an emission line, you can apply these corrections to the emission lines, and then you can kind of think about real variations in energy for that particular emission. So that's the first thing we do in Titori. That's unfortunately is the first step. So I try to pull up my old routines, and what I found in my old computer, because see, the last time I worked with Ferros was I was in Brazil, and and pretty much that's it. I did something published with TW, and there was Ferros data, but most of the work was done by Sylvia, and then I don't know, my routines and my IDL was all in Brazilian computer. I didn't transfer. And what I have here is the low resolution procedure that I use for low resolution data, which is kind of a small, not a big number of pixels. So what I did, I adapted that to what I think it's okay, but it's too manual. I think I have to do more development to make it more automatic. So what I'm trying to say is Ferrous has 180,000 pixels, and the effective wavelength we have is from 4,000 to 9,000 angstroms. So we have 5,000 angstroms, and that is distributed over 180,000 pixels. So it's a heck of a pixel. So my students, undergraduate, working with low resolution, they got tired of marking points to do the normalization that Ognian showed a while back, but that's what we did for normalization. And I don't know, what I'm trying to say is the step I am right now, and I show you the routine and the result of it, is very, very tedious. But it's helped me to see what is in the data. And and it's kind of a preliminary. So I would say I would need another week or so to make it more kind of a compact and more kind of a user friendly. But I think what we have now, at least one idea of what we can do, and then you guys can expand on how to operate that into Python language and translate that in Python language. I will pass the routines I have in IDL to you, and then you try to make something similar on it. So what I have here is the IDL, and in fact, this is not it. It's my blog. I have to take notes, so I don't know what I'm doing. And I create two routines. One, I found myself every time reading the template and reading the T-Tauri and the sun. So then I create this routine here. And the only thing it does, it reads the T-Tauri record, whatever. So there are 92 records. So record 1 is the first 2, and so on, so on, so on. And then it spits out a wavelength scale that is common for the standard, T-Tauri, and for the sun. Okay. So that if I'm in my workbench and I want to have a quick look, I can call this routine and then see the window that I'm interested outside the routine itself. But then I don't need to type the roots and all these things that take time. All right. Now the routine veiling. Let me give a little architect of it. So the routine veiling, I enter the record that I want to work with and which wavelength I will start measuring the veiling. And this parameter here is in the case the file, the observation is too noisy, and then I can do some smooth on it. In fact, oh, no. SM is for smoothing in few pixels. And OW is all the veiling calculation I'm saving in an ASCII2 file so I can see it, I can read it, and I can make modifications. And these ASCII2 files is appended with more data every time I work on that particular file. So I have to find a better way to save the veiling, but that's what I have thought so far. Now rotation is a different thing. I went online, and TW Hydra is supposed to have a Vis-Ni, a rotation. So when you look at the star, if the star rotates, you have the lines. If you think about lines with some Gaussian profile, the west part of the star is moving towards you because it's rotating, and the eastern part of the star is going away from you because it's rotating. So, and that's depending on how you are seeing this star. So you have profiles that are moving towards you and profiles that are moving away from you, and that causes a broadening of your overall line profile. So I have a routine, and this is something you guys have to find an equivalent, and I will try to find that in Python. I'm pretty sure there is some out there. I have a routine that does this broadening by applying a Gaussian filter in the data. So what I do, I take the template and I give a small rotation of the published value Vis-Ni for TW Hydra, which is 4.5 or 5 kilometers per second, something like that. TW Hydra might rotate more, but is Vis-Ni. It depends on the angle in which you observe the star, and it seems that TW is tilted towards us, which means we are seeing the disk pull on almost, and then the stars appear not to be rotating. So I entered this in here, just probably not so much for TW because 4 kilometers per second doesn't do much. But if we want to use this routine for other stars that rotate more, so we have to add some 10 kilometers per second or some procedure there. Now I have the colors going on here. So basically what this routine do is here so right here it reads the T-Tauri. My daughter was making faces here, and I make faces for her. So this is the wavelength, the standard, T-Tauri, and the sun. We don't need the sun here. And then I open this ASCII2 file that I will load the veiling. maybe you guys can find something better or clever to do with the veiling, but I want to see what am I doing. And then what you do, just to make sure I force, oh my goodness, look at the man. He's gonna be fired. He's sneaking out of a job, a work, just to do fun thing. How are you doing?
Okay,
I don't want you to lose the job, because if you lose the job, you have to work double.
Oh yeah. I have few minutes break. Just want to.
Okay, but I'm taping, so don't worry. You can check later. I'm taping.
Oh, okay.
This. Yeah.
Okay,
so then I just make sure. Ferris is not a problem because the wavelength space in Ferris is the same. It's the same del lambda. The dispersion is 1 del lambda per pixel always. But I introduced this just in case we have, in the future, we download another TW Hydra from a different spectrometer that has a dispersion that is variable. Some of these routines, especially the one that does the smoothing on the data that is too noisy, require the smoothing to be done in pixels, not in wavelength, so that you have to have equal dispersion throughout the spectra. So, but basically, this is something we don't need to worry about it. And as I said, I'm doing a rotation on the template on 4.5 kilometers per second. And then it goes to the fun part. The fun part here is to do what Ognian did with H alpha, which is to pass to find a procedure to normalize the spectra. So what I do, I'm taking a window of 25 angstroms, just to see. I mean, 25 angstroms is ridiculous. We're going to spend the entire life doing veiling, so I have to improve this and make it more automatic. But just to see where I'm going, like when you cross a creek and you don't know what is underneath, the flowing water, you do in the shallower part. At least you know where you're going, and then you can try to adventure and make it a little bit more exciting. But I want to know what I'm doing, so that's why I'm just opening a 25 angstrom window, and then I slice both the T-Tori and the template in 25 angstroms, and then I do the continuum normalization on each one of them. So how this continuum is done, I take 25 angstroms of the spectra and I mark visually 4 points like Ognian did. I think that is sufficient. But you're gonna have problems with your joints here in the finger after a while. But at least to know where we're going, I'm doing this for T-Tori and for template. And I'm making the window interactive, so that if I like the normalization, I save it. If I don't like, I do it again, and I show how that works. And I also have the ability, if that window has some spike emission line or is busted somehow, I go to another window, another 25 angstroms, and then I keep on going. So I do that for the T-Tori, and I have some option here in case I want to take a break to stop in the middle and then continue some other time. So at least for now, I'm putting that option on. So once you select these 4 points, I have a routine that saves these clicks, which is flux and wavelength, or continuum and wavelength, and do a polynomial interpolation order 3. And this is done here. In fact, here. So it's polyfit, and I think there is an equivalent of polyfit in Python. So it's just a, third degree polynomial. It's nice because I can kind of guide where to go. And then I divide both T-Tori and by the continuum, and I divide the template by the continuum. And then I find myself now with the 2 stars, T-Tori and template normalized at 1, right? and then I do an overplot on them. And just to save time, I do a cross correlation with veiling steps of 0.05, just to see which minimum chi-square comes out of applying different veilings on your template. So when it gets to the minimum point and start growing again, it stops. So I start with the veiling 0 and keep growing veiling all the way to when the minimum chi-square start to grow again. The chi-square start growing again after passing the minimum. So I don't need to keep doing a bunch of things. So in other words, you have the template and you have the tutorial, and then I keep applying veiling on the template to the point that the difference between those two spectra reach the minimum, and then take that veiling value and save it and plot, and then you see it, and then you might not like it. I remember that sometimes this chi-square would do some weird things, and then it gives me, now I open one option that gives me the ability of alter the veiling 0.1, each time, in case I don't like, just to see which one I like it. Now, when I'm satisfied, I do a click and I go to another window. And this is pretty much the procedure I have so far. Again, you guys are artificial intelligence wizards. You can find a better way to make this more automatic. But physically, that's what we do to calculate the veiling. Do you have any questions so far before I do some demonstration here?
Yeah. I had two questions. So the first one is there any significance to using a third-degree interpolation?
As far as I remember, it worked fine. I started with 2, didn't work well. If I put 4 or 5, it gives too wavy. Try to do a better job and becomes too wavy. A polynomial degree 3, it's not a parabola, right? So it kind of follow 4 points and try to minimize in those 4 points that you fix it. And it works decently. So,
okay, yeah.
I had people that try to, if you have a very nice continuum, you can take a median value over a certain number of pixels. But the problem is our star is late type. It has molecules like hell. And so you don't see the continuum. You see here and there a little bit. So you can try some different polynomials, some different procedure. So let me know, and then we can.
Okay. Yeah.
And what is the other one? You had 2.
The other one, yeah. So then, for your veiling calculation, are you doing chi-square using the line centers?
No, I'm doing for the 25 angstrom window.
So, but you're doing a chi-square for the veiling, right?
I'm doing a. Wait a second. Let me get the whole thing here. Just a minute. I'm gonna get a new one here. Wait a second. Oh boy! Wait a second. So just consider this is your T-Tori, and then you have a template. Something like that. Now, this is for veiling 0, right? Veiling 0, so there is no veiling, and supposedly the wavelengths are all correct, so things are all nicely in fit. So what you do, you take a difference of TTS minus template, and you square that thing, and this per pixel. So you take this pixel here and subtract from one another, and you keep doing all the way to the end, and then you sum this, right? And divide by the number of pixels, and you take the square root of that difference. So that's your chi-square, right? Now, and then what you do, you save this information. So you start with chi equals 0, and then you call this something else. So difference is that, and then your chi is going to be the chi you had previously plus the difference, right? And then you take your veiling is 0 plus 0.05, and then you redo this whole thing. But when you apply a veiling, your template becomes a little bit closer to the T-Tori, and then the differences will be less, right? And then you keep doing this to the point that the difference reaches a minimum value. And the next veiling you do, your template now is up here. And then the chi-square is bigger than it was the minimum one, and then you stop the procedure. Does that make sense? So it's
as if which data points are you using for your chi-square?
The TTS is the TW, right? Whatever comes from there. Now the veiling template is what you did. You take the TTS. No, you take the template plus veiling, and then you divide it by 1 plus veiling. Assuming they are normalized, that's what it gives you.
Right. But then when you actually do your chi-square, are you comparing the very bottoms of the absorption lines, or are you comparing?
No, the whole thing. You take the whole thing.
Okay.
Not just the line, but the whole thing. So if you have a junk here, that will affect. So that's why when I display the spectra, if there is a spike or some emission lines, I move to another one because it's not good.
Okay.
Yeah.
So this is done in 25 angstrom intervals?
In 24, yeah. I'm because now I can see in detail, especially if the program is busted with some bug or something. I can see where the problem is, and probably later on this has to be changed. Perhaps what I would do, I spend one day finding which windows are good to calculate veiling, and as I do this calculation, I'm saving this window in some .save file, and then when I do for the other files, I will have these windows previously saved, and then I will have my program doing automatically at least going to the windows, and that's one way to cut time. So if I know which window should I calculate veiling.
How can we determine what windows would be better than others?
For instance, a window that doesn't have a lot of a noise, a window that doesn't have some busted pixel. Sometimes you have a hot pixel and then you have these spikes that, you know, the data reduction process didn't take them out. Or you have a window that has a heck of an emission line. So you can't do much good work on that. So the way it appears, so let's say I put this 6,000 angstrom because when it's 6,000, when you start veiling 6,000, it looks nice. But we can start with 4,002. But just for demonstration, that's how the program goes. Hopefully it works. Haley is not working. Where is my window? Oh, it's coming. Well, there you go. Okay, let me move this away. Okay, so this is T-Tori, and then I mark 1, 2, 3, 4. And then I say, okay, I like that, right? And then I click on the left-hand side, and then I go to the template. 1, 2, 3, 4. So the next window, automatically, it's plotting both of them together with the chi-square. So the chi-square result is in red. The white is the house. The white is the T-Tori, and these green dots are the points where the templates were previously. Now here I'm printing out the veiling just to have an idea. So for this star record number, where was it? Record number 1 is the first star in the list. At this wavelength, see 25 angstroms there. The veiling that it would be saved would be 0.55. So this little software allows to increase veiling or diminish veiling or increase manually. So if you don't like what the chi-square did. So it gives you some freedom. For instance, if you look at these lines here, to fit them, you have to go down a little bit. But fits one but not the other. And this could be a problem with continuum determination in this region. You have some gap in there. That might be some problem with blending. But you fix one line, but then you let all these other lines kind of uncovered. So if you look at these other lines and say, okay, this, I think I'm happy here. Probably, I don't know. Wait a second there. And then you have a veiling that's 0.75 instead of the one the chi-square determined. So the chi-square looks not only at these, but also those other ones here. And see that they are kind of off. So for this star, you should reduce the veiling. See that? So the chi-square eliminates a little bit the bias, right? Because you have a 25 angstrom and it say, okay, that's what it is. But you might want to, you know, human are more important than machine, right? You might say, okay, no, I like that one better. I don't know. I don't know. It's dependent. But the main point is when we present anything, we have to give an error bar. So as you develop this technique, I think, we have to think, okay, what is my error bar? It's 0.1 Veiling, plus or minus 0.1 Veiling in 6,000 angstroms, but if I go to 4,000 angstroms, it's going to be 0.2 Veiling, you know, 0.2 units. So how that go? But let's say we are happy, and then left of it, and then I save this data, and then I go to another window now. And then I do the same for normalization. 1, 2, 3, 4. So see the polynomial degree 3. It's doing a decent job. Probably not so much here. See, it's kind of off. But and then we save it. And then chi-square put up 0.35. But you know, seems to be decent for the big lines. It seems to be not so good here, right? And then you might want to, you know, increase. I don't know. Or you might want to say that, listen, I can't see in detail this line, in which case you have to expand your window, right? And then you can work like Shaunike was mentioning. Okay, I want to work with specific lines. You could take this approach. In fact, I took this approach not with Pharos, because Pharos has too many lines, but with the data with lower resolution. I have a table of probably, I don't know, 40 lines or so, and I did the veiling for each one of them independently. So I work per line. So you could do that one too, and we see which one gives more decent result. Yeah.
I have a question. The veiling for each line would be different, right? Because, I mean, wouldn't the opacity for each line might be slightly different. So wouldn't you get a different veiling for each line?
These lines are formed in the atmosphere.
Yeah.
And and the veiling is a continuum that comes outside the atmosphere. So we have a basic assumption, and that is the template is identical in its photosphere to the T-Tauri, and this is not a good assumption. As you know, I mean, the gravity is not the same, the effective temperature might be slightly different, and that's why both you and Ognian, if you guys have free time on weekend before sipping on your beer, would be nice to see if SME can give us results, because then we could create a template, kind of a bionic template for TW Hydra, based on, I don't know, line ratios, on some photospheric line ratio, all kind of things. But that's what we got. And then you keep doing this. Let's say you're happy with that, and then you go to the next, and I put a key here to stop. Click right of the window to take a break. And then we should resume at this wavelength, so I put it there, and then we are done. But let me show you, if you go to 4,000 angstrom, it's a complicated issue. For instance, there is this spike here. I don't know what that is. So I'm going to move to the following window. So there is an emission here, and I have these lines over here. So I could try to match something here, like this, this, and perhaps that. So I'm not looking at this part, right? But my chi-square is going to be bogus. But I can try to manually find the veiling, because this region in the blue is important. The veiling is going to go skyrocketing. And we can discuss this some other time. The veiling at longer wavelength is much less than it is at higher wavelength. So if we can do a good job at a higher wavelength, we can constrain better the effective temperature of the region where this accretion is taking place.
Wouldn't it be better to go to a fifth or seventh order polynomial to do
We could. It could. Yeah, we could. We could. We could. But it's another click. Where would be another click? This is the template. Even the template has an emission there. Yeah, so that's horrible. Yeah, there is nothing there. So, which means the chi-square busted. The chi-square gave a veiling of 511. 511.
Would it be bogus to go through and kind of delete the emission, the portions of the spectrum where the emission arises?
You could, but we could, but then there's another little thing we have to click and to think about it. It's easier just to avoid windows that we have emission lines.
So do you have enough windows in the 4000 region to light around?
I don't know. I haven't looked in detail yet. Somehow we have to invest time doing that. I don't know. But this is the template. There are 2 absorption lines there. I don't know what they are. Now the chi-square worked decently, right? Sort of. We have all these spikes here that looks like noise. But you can reduce veiling. Here's the emission in the template. No, that's Titori with emission. That might be chromosphere. I don't know which line is this. Perhaps going down more. There you go. What do you think? See, you resolve those lines over here, right? But then you uncover those other ones here. So which veiling level we are? 1.75. So let's say that's what it is, and then we go to another one. Is that right? Let's see that. Click left of the window to save veil. Okay. And now we have an emission here. I'm going to go to another one. That's the emission. Okay, that's a good one. That's a good one. This is bad pixel, bad reduction. Yeah, that's not bad, but veiling 2.45. And then you guys can think if that is reasonable or not. This seems better that way. Maybe what could be done in that blue wavelength, we reduce the windows to, let's say, this is 25, 35 to 10 angstrom, and then we would open them more, right? In fact, let's see what happens if we do that. 4162, 4162, 4162. 4162. Save it. Let me write this down. 4162. And I'm going to go here in the program. And change the window from, where is it? No, I don't know what it is. Window from 25 to 10 angstrom, and then explore the blue part. Okay? So then we compile this nonsense. And then we go from 4162. 4162. One, 2, 3, 4. I don't like that, so I think I have an option to redo it again. click bottom of the window to dismiss the window, click left of the window to save, otherwise you redo the window. So I click on top and I redo the window. So 1, 2, 3, maybe 4. No. So if you want to get a good data here, no. 1, 2, 3, and 4. Okay, maybe. Oh, why did I do a click wrong? 2, 3, 4. Save it, and that should be the template. 1, 2, 3, 4. So this is, yeah, veiling is absurd. I don't know what happened. I think I clicked too much and I... Okay. So I have a window for 172, for 182. Now I have a 10 angstrom window and I can see things slightly better. It's slightly better. The veiling chi-square 2.45. So now you guys should be trained to see if you like or not. Right? So should the veiling be less? You know, have something uncovered here, or should it be more? So it seems the chi-square is doing reasonable job here. Right? 2.35, and then we save it, and then go to another window. Perhaps that's it. You go to a bigger window in the blue part of the spectra, and take a more reduced window in the blue. Yeah, we gave the same one in another window. No, that was the same.
2.5 before, right?
That was the same, right?
Yeah.
Yeah. Okay. Okay. Now we are in another window. If the vein is basically the same, or around 2.5 or less, then we did a good job. I don't like this continuum, but I don't know, maybe 1.95. So that's it. So when you have all these points that we save it, we're gonna have a big scattering. So you could use the scatter of all these different points. If you feed a spline by these points and take the dispersion as your error, that could be our error bar in veiling determination in that region. And this error bar would propagate in all the determination of flux and everything else we do afterwards. But that's the routine I have, and that's the idea. To get the veiling out of the spectra is not the clever one. I think we will stay forever calculating veiling that way, but at least we might try to get some better idea. But that's how the data you get has some meaningful result.
So if we looked line by line, that would probably take a lot more time, but we would probably get more accurate values?
It could, but not necessarily. As you see, which lines are going to peak? That's the first thing. We have millions of lines, so that's a problem. Now, if you go to lines that are intense, these intense lines, they suffer from effective temperature differences, gravity difference. Some of them are sensitive to metallicities or collisions and broadening factors, and they might or might not. I mean, the best thing I can tell you, try a method and see if it works.
Okay.
Yeah, that's the best thing to do.
Like maybe we could create like a scatter plot with the x-axis being wavelength, the y-axis being veiling, and then we look at the each line by line at different wavelengths and see the different veiling values, and that should create some kind of a scatter plot, and then maybe we could put a spline interpolation through that and see how veiling changes.
You could. And don't forget that you have 92 files to do. I mean, we can try with one, and also keep in mind the best one, the one that's really important is the blue one, around 4,000 and so. So
okay,
yeah. So I will email the routines. I try to put as many comments as I could, so that you could follow there. But essentially is assuming the two stars are in the same rest frame, just normalize them in Windows, both of them, and operate the veiling. You can try to manually come up with a veiling determination, or you can cross-correlate. Cross-correlate takes less time and is kind of unbiased. And yeah, but you might bypass that and do something else.
Okay.
Are you putting the routines in these routines in Dropbox also?
I can put in Dropbox, yes, and I can also email.
Okay.
I will open a Dropbox for the project. How about that? And then I can locate the routines there. I will do that.
Yeah. I have the that folder that I have. Every one of you are part of that. So
wait a second. Let me see.
HAVE or something like that.
So if I go to my Dropbox, this is what I have. I don't see the file because probably I deleted or something. I don't know.
Maybe you deleted the link or something.
Probably I did.
I sent you an invitation again, but it says you're already part of the. You're already a member.
I will create a folder here, and then I will share with you today, and then you let me know if you have it. Oh, I have a TTS here. Wait a second. What is this? Yeah, I don't know.
How did you get a hold of the template?
Say it again.
I put the Dropbox, and you copied them, right? You must have access to it somehow, because I put the templates
true.
in that Dropbox.
I have from. Wait a second.
Where did you get the templates? Maybe we can do it that way.
That's a good point. Wait a second. Forward, continue, Natasha, Sophia, Yahoo. From here.
There it is. There it is.
Is this the one?
Yeah. That's the folder, because that's identical to what I have.
So
yeah,
that's the one. Okay.
Yeah.
So
put it right there in this one. Yeah.
Here?
This folder.
This folder. This folder?
Yeah, sure. Why not? Because all the TW hydras. Yeah, just put it in there. Put the dot profile.
How come I don't see all the TW hydra? I have only few of them. I have the templates here.
Yeah. They're only 2 templates.
So
yeah, just put it. There's an rdpharaohs.pro. Just put the other.
Can I put it here?
Yeah.
Okay, so I'll put it there. Let's see. You find a window.
You guys have all the files. You guys told me you copied everything out, so I deleted the actual.
Okay. All right.
92 files.
That is TW hydra. There you go. And Pro. Okay, so I'm gonna take this one, this one. I don't know which one is this. Get template TW. No, this is better. No, shift. No, that's for to do the shift.
Can you move them all? You can move them all as a block, I think, because they're all related, right?
Not really. This is for the low resolution. And then I might have one of you looking into that and say, what's going on here? And I don't know what this one is. But I know this gets the template. And this one does the shift. And this one is, this get template and template. Okay, this is the one that I use for quick reading of whatever record TW I have. And this over here does the shift in cross correlation, and this does the veiling as it is now. It might have some bugs there, so I'm gonna put them in here. Point.
So, oh, wait a minute. All right. Okay, yeah.
Can you see it?
Yeah, I see it.
Okay.
Now this Veil.Pro I don't need, right?
This one?
Yeah, but no. Over in the other, where you got it from.
No, I don't know what this is. Cross correlation. Looks like a routine cross correlation. I don't know what that is. I can
go ahead and try that, because I'll take a look at it and see if I have to do anything with cursors. Or is that cross correlation? Yeah, that looks like cross correlation. Yep. Yeah.
So I put this one here. This is a node. I'm gonna add. Low resolution. Okay. Now, read Pharaoh's is a node routine that would read Pharaoh's data. So, yeah, just be careful. Those are the new ones. Let me rename this.
Old. Okay. That's the catalog.
Yeah. Now I'm doing different reading, so I think it's, yeah, there you go. And yeah.
Okay, these are small files, so I'll just leave those there for everybody to grab.
Okay. But at 6 angstrom, it looks quite well. It works fine.
What can leave is the you know that in that same directory on Dropbox, Oatmeal can put the IPython stuff, the journals, the IPYNB files.
Yes.
Yeah, he can put those there too if he wants, or he could just attach them. But if he puts them in that directory, we can all grab it pretty easily.
Well, it would be nice to open a folder for Python thing, right?
Yeah, I can make a subfolder for Python.
Yeah. Okay, look at this. These lines, certainly there is not a match. There is a match here, but this line, I have no idea what it is. Now, could it be water? That's another issue. Some lines are telluric lines, and in fact, would be nice to have. And I try to find one of these routines that, given a spectra, it identifies and marks all the lines by wavelength. You see those ones?
Yeah.
Yeah, but I can't find one available.
Did you put your telluric cleaning?
Where?
Did you clean the spectra of the telluric lines?
No way. No. But for instance, the window that has telluric lines, you should avoid, because you could pick up a line only, right?
Mm-hmm.
So, but I don't know.
So are these stars? well, these are two Telluric stars, but normally what Art and I used to do is observe what we call them water stars, but basically stars that we use as telluric standards.
Yeah.
And then we did the same normalization trick that you're doing here.
Yes.
And then we would divide the telluric lines into our spectrum, and that would get rid of all the telluric lines.
But, my friend, we didn't do the observation.
Oh, okay. Yeah, well, there you go.
Okay, let's go get a white dwarf. We mail the guy who's observed, say, you dope. How come you didn't observe a white dwarf? Oh, we can't use your nice data.
So that you guys didn't, they didn't observe telluric lines then, huh?
I don't think so. I mean, when you do, if you want to be very careful, then yes, you observe your white dwarf, and you have to do in the night. And if you are very concerned, you have to observe, in the first part and second part of your night.
Yeah. Well, it doesn't have to be a white dwarf. You can do an O star.
You can do an O star. Yeah. But when you divide, you have to be careful because O star have helium lines and emission lines, hydrogen a little bit. And yeah.
Well, you have to avoid all those. Yeah.
Yeah, it's complicated.
You have to be careful.
I think it's better just to avoid the telluric band. But again, you guys all have the Solar Atlas, right, with telluric lines. So I know it's a pain. I try to make a copy for each one of us. I have to ask permission because that atlas is immense. And you might have some copyright issues, and I can't send to Reprographic without request. So I will see. I see what I can do.
Okay. Yeah, that would be helpful.
Yeah. But that's it. That's it. I mean, more than that, if we could have for instance, we are now getting July, mid of July. Shaunak, you are traveling, right?
Mm-hmm.
Yeah.
Yeah.
Philip is still immersed in classes. So, but if we could somehow communicate again during the week and see how progress is being made, that would be great. I mean, you guys are facing the real difficulty in getting data clean to be analyzed. I mean, we are not in the analyzing part yet. We are just, okay, how can we extract the information from here? And it's not easy. You have to put a lot of thoughts and try and error, and yeah, it's a lot.
Yeah.
That's it. Yeah, you just have to look at your data. You can't just do it all automatically. You have to become very intimate with your data.
Yes, you're right. At least in this phase, I mean, if you spend a few days, I mean, full time, right? A few days just going over and get sense, and then stop and then get away, go distract yourself, play a video game, whatever, and then come back. And then the idea is, if you become so intimate with your data, so you know how to get what you want, then you can create your program to make some of your routine and boring task more automatic. So when you get to that point, then we are good, and things can be done quickly, right?
Yeah.
For instance, let's say one data you do hand by hand. You hand pick your cherries, right? And then you create a way to make it automatic, and then you compare the results of your routine automatically developed with your hand-picked results, and then you see which one match what. Okay.
Okay.
All right.
Okay. Yeah.
Okay, so I will be working off and on this project in the weekend. So, and I will be in the computer all the time. So if we want to talk tomorrow, that would be good too, or Sunday. So I'm available. But once we have veiling, at least we can measure accretion rate. So that's some product there. So that's good. and then a more probably work, probably, I don't know, if we could start measuring one line, let's say H alpha, which is the most important one, or some other, I don't know. So we reevaluate what we're gonna do next.
Okay.
All
Yeah,
right?
so I think for now I'll probably start with the conventional line-by-line approach for
There you
veiling
go.
over maybe like a small window, but then and I'll see if I'll compare the two different ways, see which one works better.
Oh,
And then we'll
what
go
I
from
mean, thinking about comparison, why don't we select? Why don't you tell me which tutorial you are working on, and then I will do the same. And then if we could get together in a couple of days and say, okay, this is what we got, and then we compare results and see if we are talking the same language. Does that
Okay.
sound okay?
Okay.
Okay. All right. Okay, so let's do that. Seems to be a good approach.
Yeah.
All right.
Do you still have that those notes when you were explaining the program, so I can take a screenshot of that?
Yes, I have a notes. You mean the one that I had in the beginning? This one?
Yeah, yeah.
I can send it to you. I like to write down things that I want to do, and so I have a problem with color. So I got these things and I put it in there. I kind of take notes of things.
Yeah, I meant when you were explaining the program and you were kind of like explaining how we get the difference, the chi-square,
This
chi-square
one?
and so on.
I mean, okay. First of all, I'm taping these, so I
I
will send the YouTube video. But the program itself has I try to put as many comments as possible, and then you guys can follow that. Oh, not this one, but the other one. What is it? Now I don't know what it is. I lost my routine really. What is my routine? Did I lose Veiling? I don't know. It should be here. Can you see Veiling?
Maybe you move.
What?
When you put them in Dropbox, did you move them or copy them?
Oh my God! I think I copied. Let me find a window. Go to Documents and over here. Here. Users. W. Go. Oh, F.
You move. So you have to copy them back. Don't move them, just copy them.
So what do I do? Okay, a second.
I think on Linux you can do a shift.
Low resolution, cross correlation, shift, get them. How about
Copy.
where is copy? Oh, copy 6 items.
Now paste 6 items.
Okay. So then when I go here, you don't see it. Read Ferris. Probably I have to call again. Yeah. Yeah, now I have 10 there. Where is it? Where is it? Where is it? Open. Okay, now I open. Okay. Whew. Okay, is there? Yeah, so I try to put as many comments as possible, and then you can follow through. You should be able to run in your IDL if you also install the other routine, the get. You already had hotbrod is already in your IDL tree, and the interpol is there. Everything should run. The only thing you probably need to fix it to run in your IDL is the root, where your files are. So this routine is inside the Veiling routine that reads template and tTori, and you have to change the root here. So that's all.
Oh yeah. How about the rotational broadening?
The rot-broad should be, because that's a Berkeley routine, and should be in their tree. When they copy process is one of the folders.
What was in an astronomy library?
Is an I think is Gibor's routine. I think
I don't have Gibor's routine.
You have in Dropbox.
Oh, I do. Okay.
Yeah.
Yeah, I'll look for it.
It's process. Let me see if I can find it.
What's it called?
PROCS.
I don't know if I have that. Yes.
That's the low resolution. Gabart, Material, Natasha, Sophia, Yahoo, Human Rights, IDL. Maybe here. EX Lupi. Process. Yeah, you have there.
Okay, good.
Yeah.
All right, cool. I'll have to remember to put that in the...
Rot.
I'll have to put that in a different tab.
There you go, rot-broad.
Okay, good.
Yeah.
Perfect.
And also they have a, I forgot, there is a shift Fourier when we do the cross correlation, and then we know how many kilometers per second you have to shift tTori to match the sun, right? When the first thing we do, and then one of the steps that I did was to once you know the shift, you recalculate your wavelength scale. So this routine here, shift Fourier, it does a Fourier transform of your template and tTori once you know how many kilometers per second that is. So basically you do a cross correlation, and then you do a Fourier transform to convert your tTori to the template, which is the sun's wavelength. But anyway, if you can work without this shift Fourier, is just saving a lot of time, but computer time doesn't seem to be a problem for us. But this process here has a lot of good things that Berkeley people were using in the past. Okay, folks. So let's get together again sometime on Sunday. All right.
Okay.
All right.
Yeah.
All of us, or just you and?
All of us. I mean, it's always good. The more the merrier.
Okay. Alrighty. So what time on Sunday?
I'm pretty much any time for me. 1 o'clock is good.
I'm going after 3, between 3 and 9. Prior to that.
You are good after 3. Is that what you said?
What's that? I'm unavailable.
Oh, you are unavailable. So for me, it doesn't matter. Let's say 1 o'clock is good.
Yeah, 1 o'clock is okay.
Okay.
Yeah, that's perfect. Yeah.
Okay.
Okay. See you guys.
Okay.
Bye-bye.
Bye-bye.
Bye, guys.